right, so this is the last lecture for CS203 this quarter, and as you can tell from the opening video, its final countdown is a song that's probably older enough, older than a lot of you. I'm not sure if it's older than me or not, but it's definitely an old song because I heard it during my childhood. So and sometimes, like when I saw this concert style setting, I was imagining that at some point when I taught a class at the end of the quarter, I can have my lecture like that in that way. But definitely not this year because we are not even allowed to see each other this year. But one thing we will do today is that we are going to take a photo together. So not sure if you have prepared your virtual background. If you haven't, well, this is the best time you can do that. But before we start talking about the most important, and today I'm going to give you some idea about like why we should, again, like we are going to drive you back home regarding why we should care about architecture and what's the future about like computer architecture. So before we start, it's always good to remind you guys where we are coming from. So first of all, last lecture we talked a lot about like parallel programming, right? Like your code is not behaving as what you expected because first of all, although we say the future is parallel, however, parallel programming is by no means easy. In a way that processor, as you can tell, we have auto-order execution, and we also learned that processor can do aggressive dynamic voltage frequency scaling when we are operating on our program. And even though there's not such a thing involved, there are still branch predictions, there are still cache misses that can change the behavior of that will change the program behavior. So it turns out that even though you think the program should act like this way, you think each instruction should take equally amount of time, even though they are the same instructions, especially for the multi-threaded setting. It's usually like we have homogeneous threads. However, it's still not deterministic because each processor, they are running at different speed for a variety of reasons. And the other thing is that on the software side, if you take my CS202 next quarter, you will learn that the operating system also has its own thoughts regarding when a thread should be scheduled. So there's no guarantee that I launch the program right now, the thread can immediately be scheduled. There's no guarantee like that. And even though when your thread or processes are scheduled, there is a chance that it could be interrupt, it could be preempt. So overall, because of this non-deterministic parallel behavior, your program is expected to have different outcomes. And on the architecture side, we can only provide the cache coherency protocol to guarantee that if you guys all pull the value from the memory location at the same time, I can let you see the same value. And I can provide some kind of consistency through fence instructions to make sure that the ordering among some instructions within the same thread or the same process won't be reordered as the auto-order execution should do. That's the basic thing. That's the only thing that the architecture to do. It's still the programmer's awareness and the programmer's responsibility to think about how to tackle these bugs. So that's why we have this class here. And so aside from that, the architecture, or say in general, the computing is right now hitting an issue of power and energy crisis. So the power means that the moment it's the amount of work that you have to you will generate within a moment. So And more power means that your device is going to be hotter. It means that you need to pay more money in the heat dissipation. So if you're designing a phone, you definitely don't want your device to be really hot. And in terms of energy, it's the amount of work, or say the amount of power, the aggregated amount of power that has been done that has been done for a period of time, or say that has been done for a job. So it's the power times execution time, and it's regarding to your electricity bill or the battery life. So we in the last lecture we have seen that lower the power consumption does not necessarily means the better battery life, because there are demos that I show you that even though I lower the frequency from 4.6 to 1.2 gigahertz, the power consumption doesn't reduce. The power consumption does reduce by a factor of 4. However, the energy consumption doesn't really change that much. So that's the crisis that we are interfacing right now. And if you are interested about that, if you have a Linux system and if you have an Intel processor or an AMD processor that is supported by the program called Liquid, you can try to see if you can try to replicate the demo that I show you in the last lecture, and the code is all online through our GitHub. So just check that, and you will have a more you will have better understanding about what's going on there. So and power and energy, that's just there's also another thing that's happening right now, is that in the past we saw the power consumption issue could be improved by the process technology. And with that improvement, you are able to shrink your chip by a factor of 2, and as well as shrink the power consumption per transistor by a factor of 2. That's called Dinadian scheduling. However, it's broken right now in a way that it's no more the case that you can always reduce your power consumption per transistor by a factor of 2. Indeed, because of the leakage power, most of the time you are going to see the per transistor power consumption is about the same. So you can only power part of them on in a full speed, or power and have to power them off, or you have to significantly reduce the frequency per transistor to make sure that your power consumption gets lower, right? So that's why we are seeing 4 trends right now in the dark silicon era, is that you are going to see processor with very aggressive dynamic voltage and frequency scaling, and or you are going to see very slow but more functional units within a die, within a chip, because we want to seek for throughput oriented design, or just let it dark. Just activate part of your circuits, but not all, or to seek for better performance instead of sticking with the sticking with general purpose processor. We are going to see more ASICs that has been designed. Okay, so by the end of the last lecture, we see 2 teams, Mystics and Valors. They are all 16 points, and which is unexpected. And today we have 4 questions, and the third rank, which is the Rocket, is 11. So turns out that there is no chance for Rocket to catch up. So this is what I am going to do today. So today I'm going to separate you guys just into 2 teams. So the Rocket team will be together with the Valor, and the Instinct will be together with the Mystic. So team 1 and team 4, you can still get a chance of participation with them to see how this 2 teams works, and get a feeling of that. Or on the other hand, you can be the spy of other teams to mess up their discussion or something else. Right? And today I'm not going to use a random number generator. So whenever the scriber of the team is ready, just raise your hand. Depending on who I saw, whose message pop up, whose hands pops up first, I will call that team. All right, so today we are not going to use a random number generator, because I just feel like it's the random number generator sometimes doesn't really looks like that random, right? So let's try to use the raise hand feature for today. All right, so today that's the only thing we are going to talk about. We are going to talk about dark silicon and its impact on computer architecture. So we talk about very aggressive dynamic voltage frequency scheduling first, but now let's talk about another trend that's called slower but more. So some of you might think that how come the frequency still have an impact on static power, and why make the transistors slower will still works? So think about this, right? So the leakage power is a lot. However, if you look at the function of leakage power, the voltage is still a very significant, it's still a factor in leakage power. And the voltage, as we said, is related to your frequency. So if you really want to lower the supply voltage, you lower the frequency is still a very effective way. So in fact, if you can lower, and this is, and when we say the frequency here, that's the base frequency. So if you force all your transistor operating in a very slow speed, there is still a possibility that you can significantly reduce your leakage power consumption. So that's why instead of seeking, so that's why if you look at the many core processors, like we have a 24 core Xeon processor versus 4 core quad core Xeon processor. The quad core Xeon processor, the base frequency is 3.2. However, when you move to the 24 processor cores, you can only put it into 2.2 because you want to make sure that the frequency and the voltage is low enough to keep your leakage power low enough as well, right? So that's why we are saying that when you have more core processor, your speed is going to be slower per core. And so if you go to like a Xeon 5 processor, which has 72 processor cores, well, some of you are I'm very excited about that. I have a 72 core processor. However, look at the frequency of each processor. It's only 1.5, and even with turbo, it's only 1.6. That's all because the leakage power limitation of dark silicon. So as you can see, right, if you really want to have more functional units or want to have more cores in your processor, turns out that you have to sacrifice the per core performance significantly, right? So from quad core to 72 cores, it's now downgrading from 3.2 to 1.5. So each core is actually like twice slower comparing against the case, right? So so if you want to build homogeneous processors, you can either have a lot of processors with slow cores, or you can have very few number of cores with very fast speed. So here comes the single instruction set architecture's heterogeneous chip multiprocessor, right? So the basic idea of the heterogeneous single instruction set architecture means that all the processor cores, they use the same instruction set architecture. And heterogeneous chip multiprocessor, it means that on this processor, we have different types of cores. So for example, what has been given in a paper is that you can use the same die area to build a quad-core EV6, like a quad-core processor with high-end cores, or a 20-core processor with low-end cores. So you can imagine this is like a quad-core Xeon, and this is like a Xeon 5 processor, right? So in the past, you can only do one of this. However, with the idea proposed by this paper, you can potentially build an 8-core processor with 3 of the most advanced core and 5 of the slower cores. So if you look at the question that we ended in the last lecture, right? This kind of combination, what it can give you. So first of all, because it's a single instruction set architecture, you don't need to recompile your code, and however, as we said, right, instruction count is only one thing, right? So it's more about the time and the time you spend on the processor core. So there's definitely no no guarantee on the energy delay. And but what's a benefit of single instruction set architecture is that if I have a process with limited thread level parallelism, I can still get benefit from the high performance core. So it would get you the same level of performance as the homogeneous chip multiprocessor because both of you have the same amount, both of you would allow the program to use the same amount of most advanced core to run your program. So in terms of performance, there's no sacrification. However, if you have a program with rich thread parallelism, then it becomes the case that it may not be able to be competitive as the heterogeneous processor. So if you look at this graph in a paper, it shows that, well, so first of all, right, the heterogeneous, so this is the heterogeneous chip multiprocessor. It does better than the case that we have quad core only because we have more cores. However, as you can see, before 4 cores, we are scaling as good as the quad core processor. And after the quad core, our scaling is the same as the 20 core, like a Xeon 5 processor. So this is the 20 core processor. Right, so so for the heterogeneous chip multiprocessor, the benefit is that as long as my thread number is still lower than the core count that I have on the chip, I can still scale well. And because I have more cores, so it has better scaling factor than the most advanced chip multiprocessor. However, if you really want to seek for thread level performance, then a processor like Xeon 5 that has a lot of slow cores still have its value. So that's why you see a lot of different kind of processors are now all in the market to accommodate the different demands of computation. So the answer to this question is actually just 1, 2. The second statement is correct. All right. So, and who is using the single instruction set architecture chip multiprocessor design? So, if you have a Qualcomm, or say if you have any Android phone, most of them would have a Qualcomm processor or an NTK processor or whatever processor. And those processors intensively use the big little system in a way that they have big cores. You can consider the big cores like the EV6 cores, and the little cores, you can consider them as the EV5 cores. So they use this kind of architecture to accommodate the different computation demands. So if you have a single threaded, single process program, then they would use big cores to deliver high latency computation. And if you have a parallel program, then or a latency insensitive program, we can schedule them into the little cores. And on the other hand, the rest of the system, they still have the GPU video, whatever, to deliver the performance of other things. So you might think that, well, why am I reading this paper? Because that paper's concept has been implemented in the processor. And in fact, in Intel's next generation processor, they are also trying to integrate the big little idea, or say in general the single instruction set heterogeneous chip multiprocessor idea in there. So this paper is definitely a must to read if you are thinking about, if you want to know, wow, why are we having this architecture? And another trend regarding slower but more is the rise of GPUs. So GPUs, people right now are thinking about them as a very powerful powerhouse powerhouse for computation. However, 20 years ago, GPU is just as its name, graphics processing unit. And the reason, and even for now, the reason why you want to get a good GPU is because we want to play games, right? So you want the best GPU to play the best game. And so the GPU is originally nothing but them displaying images efficiently. And if you think about the requirement of delivery, saying that right now you should have a GPU that's at least giving you an HD resolution and times 6 frames per second, and definitely in the era now we want like 4K, that is twice on that is like 3840 times 20 2116 pixels times, I probably want 120 frames per second, right? So to produce this, you actually need a graphics pipeline like this. So first of all, you have input and you assemble them together, and there's a vertex shader and geometry shader, and setup and rasterizer and pixel shader to and finally assemble them all together to output, merge them together. So that's the pipeline of graphics processing unit. And within the pipeline, 3 of the stages must be programmable, because for different pictures we have different requirement of this. We have different vertexes, we have different geometry, we have different numbers of pixels or different positions of pixels. So they will have they will definitely need to apply different renders, effects, and algorithms. So turns out these 3 stages give people a chance that we can reprogram the stages of the graphics pipeline. And to facilitate that reprogramming, we have to provide instructions for people to use. And that gives us the chance that's nowadays what we are using. And why we can use this 3 stages, that goes back to the basic concept of shading. So this is a surface. And for each pixel or point on the surfaces, you need the light, you need the light, and you need the reflection, and the viewer is probably from this angle, right? So if you want to calculate what you should see from for this pixel under this light, under the reflection we have, here is the formula, but because this is not computer graphics class, so I'm not going to explain that in detail. But one thing I can tell you is that all of these parameters that you see here, they are all vectors, and here, so this is our all vector operations, and these are accumulations. So if you heard like, okay, vectors accumulation, you probably would also think about, oh, there are lots of linear algebra would use this. Yes, because it's linear algebra. So we could use this feature to help us to solve linear algebra problems, algebraic problems, right? So that's why people would like to use the GPU to solve general purpose problem right now, because we see the chance of doing that. But given that we know that GPU is originally designed for graphics, so its architecture is still based on the demand what a graphic processor should have. So thinking about the nature of GPU, what a GPU architecture should look like. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, looks like we have a lot of GPU experts because you guys answered this question real quick. So, but the answer still shows quite a lot of deviations from what you guys think. So I think it's definitely a case that we should go into group discussion. So now let's have all of you go into 2 teams into discussion. Go! All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now, okay, put your hands down, Winston. Okay, so 1, 2, 3. Okay, Winston, you got it.
My team thought it was the first two, the many
The
ALUs
first two?
to
Okay.
process the multiple pixels simultaneously, and the low latency memory bus to supply the pixels, and basically the workload.
Okay, so why?
I just remember this from my GPU programming class. I remembered it used a bunch of ALUs because the calculations for the pixels are relatively simple, right? They don't actually require too much performance, so it's more about the throughput. The calculations are pretty simple, but there's just a bunch of them to do.
Okay, so you think the first two. Okay, how about Jonathan?
We also thought two, but we didn't think it was the second one because GPUs are high bandwidth but not low latency.
Okay,
And
so why don't you think it's low latency? But instead it's high bandwidth.
well, because the GPU is a throughput-oriented processor. Like if they somehow were able to fix the latency problem of memory over a CPU, like that'd be a different kind of processor, right?
Okay, so Winston, what do you think? I like to hear this kind of discussion.
I mean, I think he might be right here, but
Okay,
isn't it
so
supposed to be pretty response heavy too? Because I mean, your graphics need to be like 60 FPS, right? Or like 120
yeah,
FPS.
but okay, so that's a very good observation, right? So let's look at this. So first of all agree with you. We need to have many ALUs because we actually have a lot of pixels, right? And how about the latency? So regarding the latency, although you have 60 FPS, right? So even though in terms of latency, even though I want like 120 FPS, right? You still have 8 milliseconds latency to get everything done. 8 milliseconds, right? How slow is we say DRAM is slow, right? But DRAM is slow in a way that comparing against processors. But if you look at the latency of the DRAM, let's say like 100 nanosecond, right? That's still way lower than 8 milliseconds. So you actually don't need the memory bus to be that low latency. But instead, you want a high bandwidth memory bus to support the throughput that you need to feed the input to this many ALUs you have, right? So you don't have to make your memory bus super low latency, but you want it to be super high throughput. So when you look at the data sheet of NVIDIA or AMD's GPUs, they always talk about we have like hundreds of gigabytes per second for our memory bus, but hundreds of gigabytes per second, that's actually the throughput measurement, but they never tell you the latency of their memory because they are actually using a lot of buffers, a lot of banks to trade the latency with bandwidth. Okay, so the second is not correct. Okay, so at least we know Mystics is not getting full credits on this one. So Valors, so how about, what's the other one you think that should be true?
We thought it was the fourth item, powerful ALUs to process many different kinds of operators. Our thought was, the typical arithmetic, but also floating point stuff. And as well, I suppose the ray triangle intersect for like RT cores.
So if you look at what the computation we need to do, what do we have here?
It's just multiplications and additions and one exponent, unless that's like a norm
right.
or something.
But what your processor can do, what your CPU cores can do?
All of those.
All of those and a lot of others, right? So actually, first of all, we don't need high performance branch predictions. All of you agree, right? Because the pixel behavior is very uniform. And even for the fourth one, not really, because we only need vector add, vector multiply, maybe vector division, and low frequency is okay because we have many threads and we have a total of 8 millisecond select to get a computation down, right? So it turns out that you guys also and we don't need other features, right? So you don't need a pop count instruction in your ALU, right? Because we don't need that for graphic processing. So a lot of you think about like our GPU is very powerful, but again, right? So both of the Mystics and Valor only get half points for this question because you guys are overthinking the powerfulness of GPU. So GPU is actually, and remember what's the title here? the title in this section of trend is called slow but more. So GPUs is actually a very good example of a lot of slower ALUs, but more using slower but more ALUs to parallel process the demand of vector processing. However, if you look at each ALU, they are actually very simple ALUs, so they can keep each ALU power consumption really low. And because you don't have branch predictors, so you can spare your space for more ALUs. And because you don't have to tweak your memory bus to be super high frequency, so you can also save power consumption still. So the whole point of GPU is that we just use a lot of slow things to get good throughput. And you should have learned this in one of the performance lecture when we talk about the latency of delivering a machine learning outcome. GPU is actually pretty slow because the per LU performance of GPU is really not that great. And the operation supported by each GPU LU is also simple. So that's why we can put so many LUs within the same die, because their LUs are really simple. And if you just think about the nature of graphic processing, you don't need that many different types of instructions. So GPU is actually not that powerful as you guys think. It's just a processor with many LUs. And this is the last generation of NVIDIA's streaming processor architecture. So as you can see, a GPU contains a lot of streaming multiprocessor, and within each GPU, there is a thread scheduler to distribute those vector threads into different streaming multiprocessor, and there is a global L2 cache that your stream multiprocessor can share their data, pull data from, and there will be memory controller, but those memory controller are labeled for high bandwidth instead of low latency. And within each stream processor, there will be like 192 CUDA cores, and each of the CUDA cores perform the same operations, and each of this is also a thread. And you have a total of 192 cores, and so that's the GPU. And as you can see, right, because if you have low latency LUs, then your voltage could be really low in this case. Although now GPU is also pretty power hungry, because we try to tweak each LU to be gigahertz level, and we had thousands of LU on it. But presumably you can also it's still if you want to build the same amount of LUs using CPU cores, that's not possible because of the complexity of each LU. So GPU is actually another example of slower but more. All right, so big little core or GPU is an example of slower but more. And we had this design, we try to shift our computation for that because of dark silicon. And another thought about dark silicon is that why don't we just let those chip dark? So what's that? So if you look at NVIDIA's Turing architecture, and if you look at each GPU cores, each CUDA stream multiprocessor, in addition to those CUDA cores operating on floating point 64 or integers or floating point 32, they added the new stuff called tensor core unit. So, and if you look at the probing model they used in the past, is that saying that if I want to use cupolas, I can set the mask mode to use tensor cores. And what does that mean is that depending on the power consumption of my and to use tensor cores, you have to make them you have to make your number 16-bit, because tensor cores is actually a set of matrix processors that only accept 16-bit numbers. And then you can perform the GNN operations on those tensor cores. However, the reason why if you want to use tensor cores, you have to set the mask mode is just because tensor cores, usually if you don't activate it, in Turing architecture, they will turn it off. And the reason why we turn it off, because when we don't use it, we just turn it off to save the power. And if you choose to turn on the tensor cores, or or the default math mode for cuBLAS right now, they are going to schedule those matrix multiplications on tensor cores, and only if we have free power that could be used to activate the rest part of the circuit, like for example, your floating point units, we will use the floating point units. So what would happen is that when you are manually use tensor cores, the rest of the circuit is actually turned off to save the power consumption. So so there's never a chance you can turn on all the tensor cores plus all the floating point units or integer units on your NVIDIA GPU right now. It's either all of this plus some of those, or all of this, all of that plus some of this, but not all of them. That's also because of the dark silicon influence. So that's why NVIDIA's Turing architecture chose that. And however, because the process technology allowed the chip designer to put more features in there, like matrix multiplication features in there, so they still think it's worth a while to add that feature in, but dynamically turn it on and off. And another example that I originally want to put a slide in there, but for companies like Apple, they are pretty secret about their design. But a lot of like Apple fans, like Apple has the M1 processor, Apple has the A14 Bionic processor, and what this processor all have is some kind of AI accelerator. But are you going to use AI features all the time? Not really. So what will happen on this processor is also the same. When you are performing AI operations that could be using those AI accelerators, I would turn on those chip units. But in the meantime, because you are not using those chip units to the rest of the chip units to perform the task that you are using, so I can lower the frequency or even turn off those processors that are not in use to save my total power consumption. So that's another example of that in dark. However, because Apple is very, very, very secretive about their design, so there's no way we can prove that, but that's my hunch. All right, so that's another trend. So now let's go to the last trend that I want to talk about in this class, and that's actually a very important trend, is the rise of ASICs. So ASICs is the application-specific integrated circuits. So so what's the idea of ASICs? So saying that if we have a feature saying that we have a computation called AI plus equal to AI plus 1 times 20, that's the computation I want to do all the time. So if you want to use RISC-V to implement this function, you probably need 6 instructions, right? And you can pipeline this 6 instructions like this. And if you want to design a processor that would support this RISC-V, all the RISC-V instructions, this is the processor you have, right? So turns out that you have a big processor with big circuits with that, and you need a total of 10 cycles to execute this 11 instructions, right? So, but if you think about, if that's the only feature we want to execute, right, we can actually spatialize the circuit a little bit, right? So first of all, if that's the only instruction type, the only type of instruction that I want, then we don't need the instruction fetch unit, given it's just a fixed function, right? So we can totally eliminate that to save the space on our chip. And if you have fewer circuits, you can make this design more power efficient. And now, thinking about you only want to do AI plus equal to AI plus 1 times 20, right? And 20 is actually a constant. And you only need one value, one register to save your accumulation. and one value for your current input value. So you don't need many registers. You probably only need 2 registers at most. And so you can significantly reduce your instruction decode. And you don't have that many other instructions, so you don't have to decode, right? So you don't need a giant logic for decode, right? And so this is similar to what a GPU used to do, right? So for GPUs, you only do vector multiplication, addition. You don't have branches, right? And because you are only going to perform these instructions, so you don't have to worry about the hazards. So this could be eliminated. So your circuit could be again simplified like that, right? So if you have the pipeline like that, right? So this is what you end up with, right? For these 6 instructions, this is essentially the circuit you need. So comparing against a full-fledged general purpose processor, this is what you end up need. So if you only need this, right, you can again still pipeline it, and because between each pipeline you only have fewer amount of things to do, so your frequency could be higher, and you can still pipeline it, and and you can still pipeline your task like this, right? So turns out that your throughput will be a lot better. So this is the concept of ASICs. Then that's why you can get a better performance if you reduce the amount of features or focus on the most important features of your computation when you design a chip. And because the circuit is a lot simpler, so each unit could be less power consuming, and you can put more on the same die to make your design more efficient. So in addition to graphic processing unit, we know there are a lot of other workloads that we care about nowadays. So this paper by Google, you see a lot of authors on this paper, right? So, but you still can know a few like names that you already know, like Noam Chomsky. We just read his paper with Dean Townsend on heterogeneous chip multiprocessor. We also read his paper on prefetch buffer. So you know he is really a big player in chip design. I hope maybe one day I can invite him to give a talk, right? And there are also other people like here, David Patterson. He wrote a textbook, right? So now you know, like, oh, Google hired a lot of great architects to design this tensor processing unit that we call TPU here. So, but why TPU is so critical to Google nowadays, and what really is a TPU, right? So now I want to invite you to look at this question and tell me what's the monster that Google designed. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now I think it's a good time to have a group discussion. So go. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so now raise your hand. Okay, Jonathan, you are faster today. Okay, so what do you guys think?
So our group thought it was 2 items, dense matrices, and the majority of the TPU's area is used by memory buffers.
So which one?
2 and 3. So
2 and
answer
3.
C. Yeah.
Okay, so why don't you think the first one is necessary?
Well, because it's for short, like unprecise methods, or sorry, unprecise data points, like int 8 or something like that.
Yeah, but why they designed to the TPUs to work on int 8 instead of like more precise data types?
Because aren't more precise data types very expensive to?
Yeah, but why they can do that? Okay, Daniel, you are going to help. Hello?
Oh yeah, sorry, it popped up on a different monitor. But since they're built to accelerate like inferences, and those use like 8-bit integer data types and stuff like that. Nothing very long, like 64-bit.
Right, but why inferences could be using 8-bit integers?
I don't know exactly why, I guess.
Okay, so the whole thing about machine learning, right? You guys think about like machine learning is very compute intensive. Well, in some sense, but however, machine learning is not really an application that, well, depends on where you use the machine learning, but in a lot of cases, machine learning are pretty error tolerant. So for example, if like in the morning all the time, it happens all the time that I look at my iPhone, and if it doesn't like unlock, I would just do it again, right? So what does that mean is that, okay, the user behavior are really tolerant to inaccurate machine learning outcome. So the same thing is that, and Jonathan, I think, and Daniel, you both said one thing right, is that if you only support 8-bit, it will save you a lot of spaces in LUs so that you can be more energy efficient, power efficient. However, why we can do that is because we know for those applications we have doesn't really care about the accuracy that much. So again, for the GPUs, they can choose to implement their ALU for slowly because we know that the user is not going to use that result for 8 milliseconds. So as long as you can get a result out by 8 milliseconds, that's okay, right? And for TPU, it's the same. We know that, well, most of the time it's accurate. Maybe once in a while it's not accurate, that's okay. But if we allow that inaccuracy in some cases, that would allow us to use lower precision data type. So first of all, TPU is nothing about like highly accurate computation. And it's only supporting very low, very imprecise data types. And a lot of you care about sparse matrices, but TPU is designed for dense matrices because it doesn't make sense for the TPU to deal with the complexity of sparse matrices if we already can speed up the matrix multiplication by a lot. And a majority of TPU area is used by memory buffers because your input data is really large. So how about the fourth statement, Jonathan? What do you think?
Our team was unsure, so we defaulted to not true.
You defaulted to not true. Okay, so Winston. Okay, the chance of mistakes.
All right. Our team also thought it wasn't true, but not because we guessed. Joshua brought up a good point. He said it's the instructions aren't equally long because it's a complex instruction set.
Okay, right. So I would give. I feel it's a tie again, right? So I would give each team half points for this question because if you read the paper carefully, the TPUs they are using so-called CISC instruction set architecture. A lot of people think about like, oh, CISC, it sounds like outdated. However, again, if you look at the figures that I draw here, right? We are actually designing ASICs, right? The TPU is an ASIC for machine learning. So this TPU, it supports things like convolution. It supports things like matrix vector multiplication. It supports like ReLU. It supports like hyperbolic tangent. And each of this, right, is so hard to, if you want to implement those features with general purpose pipeline, then turns out the pipeline would be super complicated. So it turns out that they design a few ASICs, a few this kind of pipeline like I show here. And each of the pipeline is dealing with different instructions. And each of this spatialized pipeline, they have different lengths. So it turns out they have to use the CISC design to make their instruction not equally long. And even though each instruction, and another thing is because thinking about these operators, they have different inputs and outputs requirements. So it's almost impossible to make them equally long. So you guys are right that this question, we have two answers correct. And look at the TPU. This is the early version of the TPU. They have the new versions of TPU now. And the floor plan, as you can see, right, they're matrix multiplication unit is about 24% of the die area, but the unified buffer, which stores the matrix data, is 29% of the chip. And so memory is actually a big part of their chip design. So for this question, 2 of the statements are correct. And look at their experimental result. If you look at their design, because it's a spatialized unit, so it actually has the lowest power consumption. And if you look at the performance, and this roofline figure tells you that the TPU has the highest potential in executing all the machine learning workloads. And this graph tells you the tail latency. And the tail latency means that the 99 percentile response time. And it's a little bit interesting here that if you just look at the tail latency, it seems like the GPU's 99% response time is better. But if you look at the batch size, GPU is achieving this 99% percentile response time with a small batch size. But for TPUs, the same level of the response time could be achieved with a large batch size. And if you are not familiar with batch size, it's the amount of work that we are doing at the same time. So what does that mean is that given the same requirement, the same level of the response time, TPUs can give you a lot higher throughput. So, and that's because the TPU actually make the tail latency better. And what is tail latency? So the tail latency means that what's the worst performing cases in all the test cases. So if you have 99% of the server's response time is 10 milliseconds, but only 1% would take 1 second to respond, then if you want a whole batch to be complete, saying that, okay, so the criteria of finish this job is that I want everything to be finished. Then even though 99% of them will take 10 milliseconds, but only if 1% of them would take 1 second to respond, you still consider that the whole batch of the job is spending 1 second to respond. So what does that mean? Is that if you have 100 tasks, even though 99% of them, 99 of them can finish within 1 second. 60% of the time, your request will take more than 1 second. So that's the influence of tail latency, right? So that's why people talk about tail latency all the time, because if a job within a batch cannot finish within with very short period of time, the whole job, the whole task has to wait for the slowest one, right? So that's the influence of tail latency. So TPU has better tail latency. And well, after reading this paper, right, NVIDIA is really angry because NVIDIA think, well, we are the leader of machine learning. So they try to give you guys a lot of different numbers to tell you that, oh, okay, we are doing better in a certain way, right? And that go back to the paper that we read a long time ago, right? Is inferencing per second a good thing, right? Is training TOPS or inferencing TOPS a good thing to look at, right? So it turns out that I don't think there is a clear winner between TPU and GPU, but my feeling right now is that if you are talking about inferencing, TPU is probably a better choice. If you are talking about training, then depending on the model, sometimes GPU is better, sometimes TPU is better. All right, so there are fallacies and pitfalls about this paper, because this is the paper by David Patterson. So when I read this paper, I feel like, oh, I'm reading the architecture textbook anyway. So they also point out a few fallacies and pitfalls. For example, they are criticizing the GPU architecture. But one thing that we should learn is that a lot of us are thinking about like risk is a more advanced design. But really, for the TPU cases, 6 is more important. 6 is a better fit because, as I said, it helps us to make the instruction units more specialized to take benefit from the ASIC design and make it more power efficient. So a lot of you are thinking about that. I learned this concept and I apply it all the way to the end. However, it could be a disaster because a lot of design decisions, not just software, not just hardware, but also software, could be case by case, depending on where you want to apply it to. Like a lot of programming principles that I taught you in the class, they are really good for performance tuning, but not for software engineering purpose. But if today your goal is that I want to save money for the company, I want to make the program fulfill the requirement of response time, you should really go with the way that I taught you. But if today your company doesn't care about performance, your company has a lot of money to waste, a lot of money from the capital to burn, okay, go ahead with those software engineering principles. I'm totally fine with it. So what usually a big company would end up with is that in the very beginning, they are very feature driven. And in that sense, in that phase, their code are very software engineering oriented. However, at some point, they have to be responsible for their stockholders, so they become more performance oriented. So one example is like Google. In the past, they have their own coding style, but now they hire a lot of architects that even do this hardware stuff themselves. You can see they are changing themselves to be more performance driven because more higher performance or lower energy, lower power could help them earn more money. All right. So now another company we want to talk about is Microsoft. So Microsoft doesn't build their own chip. They use the FPGA approach. So why are they using the FPGA? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. For this question, well, unfortunately right now there is an issue on my computer, so I cannot even, oh, here we go, finally. Okay, so I wasn't able to pull out the screenshot right now, but I guess you guys probably have an idea. So why don't you go ahead and discuss? All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay. Okay, all of you put your hands down. Okay, so let me count. 1, 2, 3, go. Okay, Andrew, you got it. Okay, so mistakes. You guys really have like a lot of people trying to nail this question. You really want a gift card. Okay, Andrew, what do you guys think?
Our team think the answer is D, flexibility.
But how do you know this? Why not cost?
Cost. Our team think if Microsoft wants to save the cost, then they will choose ASIC, since ASIC, use the full functionality of the hardware instead of wasting other resources to maintain a specific functionality.
And how about the performance?
I guess it's also the same reason. I think ASIC will eventually, or our team think ASIC will eventually outbid the FPGA on performance-wise.
How about scalability?
I guess maybe also the same reason. Even FPGA also have kind of scalability, but I don't think it can outfit ASICs.
Okay.
Yeah.
So easier to program. Why not that?
Definitely not.
Because you have to use Verilog, right? So, but why flexibility? Where do you find the evidence of flexibility?
I guess it's somewhere in the paper, and also
so it's actually not just somewhere, right? It's a lot of places in the paper, right? So the model offers significant flexibility, flexible in assistance, sufficient flexibility. And there are so many flexibility that they talk about FPGAs, right? So, okay, thanks, Andrew. And this is the last question. So I guess we know who is the winner. But before we announce who is the winner and a lot of other things, we still have to finish discussing this paper. So I don't know how many of you attended the talk, the very first ECE seminar, which also I hosted this quarter by Derek Cho. So Derek Cho is also one of the author in the paper that he is the leader who built the cloud acceleration architecture for the Microsoft. And FPGA, not sure how many of you know this, is an array of lookup tables, and you have to use Verilog to program it. And Microsoft actually used the FPGA a lot in their data centers by attaching an FPGA to each machine. And they used the FPGA to accelerate some of their services, for example, like search, and help to accelerate their, or say offload their network processing and develop their DNN network. And the reason why, and with the FPGA, they can improve the tail latency. So performance is definitely something that could be considering. However, it's not for all of the cases. If you look at what they talk about like encryption and decryption, right? On a Microsoft on an Intel processor, it takes about 4 microseconds. But if you use an FPGA, it takes about 11 microseconds. But why they choose to use FPGA to add latency to their network processing is because the FPGA actually save some of the save more CPUs resource for more useful workloads. So performance is not a reason, because FPGA doesn't always give you better performance, for example, like encryption, decryption. And because FPGAs are actually pretty expensive, a good FPGA would actually cost you like thousands of dollars. So FPGA, long term, the cost could be lower, but in the short term, it's actually a lot of cost. And if you think about the Google's TPU, like a Google Edge TPU is only about like $30 that you can purchase right now. So it's actually not, if you put into mass production, FPGA is actually not really economical wise more efficient than others. However, because they have the capability to offload the CPU, and another thing is that because you can reconfigure a single FPGA to many different functions, so it turns out like an FPGA can be used for DNN, they can be used for network encryption decryption. So that's why turns out that they chose the FPGA. So the reason why they use that economics, it will work, but it's a long-term thing, right? And but the most important thing why they chose that, because it's flexible. All right, so now you have seen that. So the final words I want to give out for this class is that computer architecture now is more important than you could ever imagine. And being a programmer is easy. However, you need to know a lot of architecture to be a performance programmer. Like in the class, we have demonstrated the effect of branch prediction, the effect of caching, and we are now in a multi-core era. You want to get your program correct, you have to put a lot of effort. And we are also now in the dark silicon era. So single core doesn't get any faster. Multi-core isn't scale anymore. We see more and more ASICs. So you need to write more code to interact with those ASICs to deploy your service in data centers. So that's really important. So before I announce the rest of the things, I want you to turn on your camera right now, but it won't be broadcasted. I just tested. So right now, please turn on your camera. In the meantime, that I will take a group photo together. And it's important because I found like this quarter, I wrote a lot of a reference later for people, but I don't know if, I don't even know if my students are male or female because I don't have a photo of it. So it's definitely a good thing that we have a photo together. So I know who you are. So I know like I should use she, him, or they, or whatever during our, you know, like class. And to be fair, I'm also opening my turning on my camera so you know, wow, what Professor Usagi looks like at the end. All right, so it's a fair game, right? So everybody turn on your camera right now. And I'm going to take the screenshot on Zoom real quick. Okay, come on, 1, 2, 3. Okay, I got a photo. Okay, cool. So now you can turn off your camera if you don't feel comfortable to turn on the camera. And I am going to continue the class. Okay, so another thing that you guys care about, right? Who won the matrix? Who won the matrix multiplication contest, right? So we actually used 4 cases and we took the average. And here is the winner. So the honorable mention is Wang Zhongqi. He got 4 times speed up on all the test cases on average. And he used loop unrolling, swap the order of inner loop. The runner-up is Winston. He got 4.07, loop unrolling, memory prefetch, very fine-tuned block size. And the top winner is Calvin. He got 4.27 times speed up with very intensive function inlining, loop unrolling, data packing, use registers for partial sum and as well as prefetching. Okay, so this is the matrix multiplication. And you know, for the team, the winner is this guys, and give you guys an applause. And there is a feature on Zoom. You guys can do that, and you will receive a gift card pretty soon. Probably not after the end of the week. So finally, the most important thing, the final. So the format of the final, we have multiple choice questions and 20 multiple choice question, homework style question in 2 problem sets. And those are your MSCS comprehensive exam questions. And we have open-ended brief discussion questions. And so there are multiple choice questions. I gave those sample questions, and you can definitely find this from the slide stack I sent you. And there are free answer questions like this, like register renaming, scheduling how many cycles it takes to issue all instruction, and what if it's in a steady state. And draw a pipeline, draw a data dependency graph, and find the best cache configuration for a pieces of code like that. Or if I give you an address sequence like this, if the hit ratio is like this, can you guess what's the cache configuration? So these are potentially the question that you should be know how to deal with. And we also have other open-ended questions like, okay, those are basic ones, code and cache miss rate, and the branch prediction, and a question that we mentioned, SMT and CMP, which one is better? Or I have 2 papers for you to read, and definitely this one would be on the final, like recently Apple have the M1 processor, and they abandoned the Intel processor, but they are still allowing to run like x86 programs on it, right? So it sounds like instruction set architecture is not important anymore. So do you agree or don't you agree with this? So this 2 paper provides you some insights. And we talk about meltdown and Spectre attacks and what features in architecture cause that to happen. And what compiler optimizations would not be effective if you have an older processor. And a few trends in dark silicon era. And if you are going to design a machine learning hardware, what do you want? And if you have a processor with many-way SMT, are you going to give the processor more cache or better branch predictor? Can we focus on improving the throughput of computation instead of latency? What's an application won't work in this way? We have many branch predictors. What's the programs? What's the pros and cons using perceptrons? And finally, the announcement, we will have evaluation due until December 11th, the best chance to boost your assignment. And the last office hour by me today will be 2 p.m. to 4 p.m. And the most important thing is that I really enjoy this quarter, and thank you all for this great quarter. And I hope that I can see you in person pretty soon. And sorry for taking 3 more minutes for this lecture, but it's really a great experience of having you all as my students. Thank you all. And if you don't have any question, or if you have any question, feel free to use my office hour. And if you don't have any more question, enjoy the rest of your quarter and the holiday season.